graph, okay, that we draw without the direction. And generally, when we have the non-directed, undirected graph, okay, we should assume that it could go on both direction or either direction, as if we consider the flow. But if we have the digraph, okay, that means the edge possesses directions. So isomorphism concept now require further consideration or further look into the direction of flow. Okay, basically it's directed of edge, or we call arc here. Okay, the head and the tail arc have significance and isomorphism property, as we should realize from that. Okay, so two digraph are isomorphic if there is an isomorphism f between their underlying graph that preserve the direction. Okay, preserve the direction here. Okay, of each edge. Okay, so that is E is directed from U to V if and only if the FE, the mapping or the biject of edge, is directed from FU to FV. Okay, so in this one, we must make sure that the graph must have, okay, in results, as a result, must have the same in degree and out degree format. Okay, so if we look at 6A and 6B, okay, another pair is 6C and 6D. So without the direction, these two graphs obviously is isomorphic. But if the edge has been assigned with direction, okay, for example, 6A and 6B, three edges. Okay, so if we consider degree, it would be undirected version, but in degree and out degree. So you can look at this one as, okay, 1, 2, and 3, and A, B, and C here. Okay, if we try to map them, okay, between 1 to A, 2 to B, 3 to C, for example, with undirected arc, it could be okay. But in this case, if we look at the directed, okay, A has 1 in degree, 1 out degree, right? As well as 1 in degree and 1 out degree. 2, okay, 2 has 1 degree and 1 out degree. C has 1 in degree and 1 out degree. Whereas in graph 6b, you see that A is the only one that have 1 in degree and 1 out degree. But B and C, okay, B has 2 out degree with no in degree, and C has 2 in degrees only. Okay, so this one you can see obviously that 6A and 6B are not isomorphic. Okay, so 6A is not isomorphic to 6B since in 16A, sorry, 6A. Okay, sorry, I think should be this one. I think lots of mistakes where this 6B. Okay, can you correct this one? Sorry, I haven't checked the misprint. 6A and 6B. 6A, each vertex has 1 in degree and 1 out degree, whereas 6B, one vertex has 2 out degree and 1 vertex has 2 in degree. Similarly for C and D, okay, you can spot C and D. Okay, this one, in this one is 1 out. Okay, so this one, 2 in, 1 out. Okay, and 1 in, 1 out. Okay, this is 1 in, 1 out. Okay, this is 2 out, 1 in, which is completely different from the C. So this one, 6C and 6D are not isomorphic. Okay, here. Okay, so clear about the digraph consideration. Okay, so now we have considered both undirected and directed graph. Okay, so if we have undirected graph, mainly we concern based on the number of vertices, number of edges, as well as the degree. Okay, and with that, we look further into the conservation of adjacency and non-adjacency as well. But digraph look further than that, okay, further than that, because when it's talk about directed graph, we talk about the flow, okay, the head and tail of the graph are important. Now we have the isomorphism problem, okay, graph theoretic discussion. General problem that may be raised regarding isomorphism is to check whether or not the two graphs are the same, or two graphs are isomorphic, okay, or the two graphs could be drawn in various ways that could cause confusion if considered promptly. Okay, we have to look further, because if you draw differently, you may say this is two different graphs. Okay, without counting the number of edges, okay, or number of nodes. Okay, but if they are the same nodes, the same edges, now it could be the same graph. Generally, we may need to check vertex bijection. Okay, as the concept that we have discussed so far with vertex bijection, as well as sometimes we may have to look at edge or the edge bijection as well, in case that is multi-edges, right? For vertex pairs, adjacency and non-adjacency properly must be preserved. Okay, so this is what we have discussed. Okay, by doing so, it means that most cases that we need to examine based on brute force approach. You can see that no way to avoid the brute force many times, because as we see so far, we haven't got any algorithm that would be used to check or automatically or effectively check the isomorphism. Okay, so we may have to use brute force in many cases to compare the sequence, okay, or order or arrangement of the vertex or level of vertex. Okay, in most graph isomorphism problem, the researcher and mathematician were trying to devise a practical general algorithm to decide whether the graph is isomorphism. Okay, that so far, okay, to prove that no such algorithm would exist. I'm not sure whether you could come up with the algorithm that would prove that would be possible, okay, in your research in the soon future. Okay, if you're interested in the graph theory as well as the isomorphism topic. Okay, so this is very fascinating, but eventually it requires brute force to check. Okay, if you have the big graph. Okay, so we have something called automorphism or symmetry. And this one is like you have one graph and you want to draw that graph in different format of labeling. Okay, so this is called automorphism. Auto is itself, right? So we're talking about isomorphism of two graphs, but there is another isomorphism problem class where a graph may isomorphic to itself. You want to draw something by starting off a certain graph, but you want to draw differently. Okay, it's like dividing a graph into another graph. Okay, but earlier we talked about we have two graphs and we want to check whether they are the same. Okay, but this one, if you have one graph, you want to find alternative way of drawing it or alternative ways of assigning the labels to the graph. Okay, so a graph could be drawn in different ways. It depends on whether it's simple or multiple graphs, okay, that you want to draw. Okay, so basically we just do the permutation and cycle notation of the label. Okay, and you just move around. When you rearrange the label, now you can see that you can draw different ways. Okay, it will look different. Okay, the product of this joint product could be used to show the presentation of this permutation. Okay, so let's say we have the x comma y, means the vertex x and y are swapped, okay, among those list of vertex x 0, x1 up to xn minus 1. Okay, it should be, I should write x0, x1 up to xn minus 1. Sorry that I didn't put it into the subscript. Okay, it's just like you have vertex x0 up to xn minus 1 are cyclically permuted so that xj, okay, and xj plus 1, okay, would be rearranged. Okay, okay, in this one we just want to swap around. For example, if you have 1 2 3 4 5 6 7 8 9 in original graph, you want to rearrange, okay, the label into different value, different number, different label. In this case, you can see that permutation has disjoint cycle form. In this one, we can rearrange the label into different label. Okay, so earlier, if you have a graph and you have 9 nodes, okay, you give label 1 2 3 4 5 6 7 8 9, and in this case you can rearrange those labels, okay, into a new one. So this one, you can see that it would be permutation of this disjoint cycle. We can divide it into 3 cycles of this kind, or you can do different ways. Okay, you can do like different disjoint cycle. But if you look at it particularly, when you want to map like 1 to 7, 2 to 4, 3 to 1, 4 to 8, 5 to 5, 6 to 2, 7 to 9, 8 to 6, and 9 to 3, what would be the valid automorphism is you have to have the cycle within those rearrangement of the label. Okay, so in this one, you see that we have the first cycle is 1, 7, 9, 3. Okay, and 2, 4, 8, 6, and 5. So we have 3 disjoint cycles here. Okay, so what do we have in this one? 1, 7, 9, 3. Look at this one. 1 map to 7. And when you look at 7, 7 map to 9. Okay, and 9 map to 3, and 3 map to 1, and 1 map to 7. So that would be cycles of mapping. 1 map to 7, 7 map to 9, 9 to 3, 3 to 1, okay, 1 to 7, and so on. 7 map to 9, and so on. Okay, and another cycles that we have seen here is 2 map to 4, and then 4 map to 8, okay, and 8 map to 6, okay, and 6 map back to 2, okay, and 2 map to 4, and so on. So this would be the green cycles. Okay, try to check that yourself. And 5 map to itself. Okay, 5 doesn't change. Okay, 5 map to 5. Okay, so now we have 3 cycles of rearranging the mapping of the cycles. Okay, so here, yes.
Professor, I'm confused at that point that why we don't use 5 in the order, like you use 1793. Why wouldn't we
Yeah.
use 1593 or 1753?
So it depends on the picture as well. It depends on the figure. I will give you, because I haven't got it on hand, but I'll give you some example of automorphism in the graphical representation. But once you have the graph, okay, one graph, and you want to reassign the label to be differently, okay, so like this is another graph that would be isomorphic to the original graph. Okay, so automorphism is talking about the relabel, okay, or rearrange the label into another graph. Okay, in this one, generally when you do that, okay, the graph would appear as a valid relabeling of the graph would be appear as the permute, okay, of this joint cycle in the graph. But the arrangement of the cycles could be different, okay, from one to another. Okay, you can see that here in this example, the arrangement of the label has been come up as 3 different cycles. 1793 is swap among these 4, and 2486 swap among these 4 in the cycles. Okay, like for example, node 1, node level 1 in graph, original graph. In the next graph, we have 1 replaced with 7. Okay, and 7 in original graph would be replaced with 9 in the new graph, and 9 in original graph replaced with 3 in the new graph, and 3 in the original graph would be replaced with 1 in the new graph, like that. Okay, so it'll be cycle of 1793. And in the another cycle within the graph is like level 2 will be replaced with 4 in the new graph. Okay, like for example, you're gonna have something like this one. Okay, can give you 1, 2, 3, 4. Okay, if I relabel that to 2, 3, 4, 1, like that, and you label like 1, 2, 2 to 3, 3 to 4, and 4 to 1, like this. This is the mapping. So you see that it would be one cycle, right? Okay, and map directly like this. okay, to isomorphic. So the left one is original, and I want to change to another graph that would relabel the nodes. Okay, so we would have 1 to 2, 2 to 3, 3 to 4, and 4 to 1, and 1 back to 2, and again. This is one cycle in the relabeling, in the permutation. Okay, Imran.
So
Yes,
you want to say that from the matrix we can conclude the cycles of the graph, the relation of the graph.
Yes, that's right. It's only 2 rows, right? Only 2 rows because the first row is the label, the list of the label, and the second row is the new label of the nodes of the same. You just have the same drawing, right? Okay, but we don't move the location of the nodes, but we just relabel the nodes. Okay, let's try. Okay, let's more complicated one. One, two, three, four, five, six. And if I want to relabel this one, okay, we're gonna have like 4, 5, 6. Let's say 2, 3, 1, like that. Just flipping, right? And we map directly like this. How many cycles do we have this in this one? You can write 1, 2, 3, 4, 5, 6, right? The first one. What about the second one? What would have? Would I have 6, 4,
4, 5,
5,
2, 3,
2,
and 1.
3, and 1. How many cycles do we have here? We have 3 cycles, right? 1, 6, 6, 1, 1, 6, 6, 1, and we have 2, 4, 4, 2, right? And we have 5, 3, 5, 5, 3, right? This is 3 cycles. Okay?
Yes, Professor.
Okay,
1, 6,
so this
2,
is
4,
called
3, 5.
automorphism, right? Okay, you just have the same graph, and the outcome of another graph would be exactly the same because we don't want to mess around with the location of the nodes, but we just relabel them to be different. Okay, and generally we're going to use the number to do that. Okay, or you can use letter, and the letter A map to another one. It would perform like linkage from one letter to another letter and back to the origin one, so that you form the cycles, right?
Professor, so we can simply say that there would be replacement of each node with a different one.
That, yeah, you can have different
Not the
format.
same.
Yeah,
Okay.
you can see that sometimes we have 3 cycles. Sometimes when you rearrange, you can try other ways, like in this one, 1, 2, 3, 4, 5, 6. If you rearrange and make sure that they can map to another sequence, sometimes you might not have 3 cycles.
Okay.
Okay, so if I don't swap 1 and 6, I still keep 1 and 6 at the same place. Okay, 1 and 6 would be the same value, right? 1, 1, and 6, 1. So in that case, we're going to have 4 cycles, 1 to 1 and 6 to 6. But 2, 4, 4, 2, 5, 3, 3, 5, right? Okay, something like that. Okay, so it depends how you assign or how you rearrange or permute the label. Okay.
Yes, okay, Professor.
Okay, so maybe in the question I can ask you, try to give me a new automorphism of a graph and show me how many disjoint cycles that you would get from this permutation of the label, right? Okay, so you can produce different series of adjacency and non-adjacency, okay, in this graph. Okay, previously node 2 would be adjacent to 1, 4, and 3. Okay, in the bijection here, we have 4 adjacency to 6, 5, and 2, for example. Okay, and mapping should maintain Okay, by default, this is the automorphism. By default, the adjacency and non-adjacency must be preserved in the graph. Okay, so this is just how you derive from one into another graph. If isomorphism, we have two graphs to check. But automorphism, we have one graph and you produce another graph. Okay. Okay, and now we move on to another topic called subgraph. Okay, subgraph is, actually subgraph is really a basic concept, that you may intuitively know what this subgraph is. That may be stated earlier. However, this may be lost any continuity to state it here, might not be lost, Subgraph is a graph is H whose vertices and edges are all in G, They might not have the same number of vertices as the original graph, could be subset of those, Some of those will appear in the new graph, H is the subgraph of G, so G would be called supergraph of H, So we have like bigger one and smaller version of those, subset of those, For example, we have 7a, to graph H1 and H2 are the subgraphs of G. You have G that all the nodes in H1 must be in G. All the edge in H1 must be in G. Similarly, all the nodes in H2 must be in G, and all the edges in H2 must be in G. If in H1, H2, if we have extra node or the extra edge that not appear in G, we call that H1 and H2 are not the subgraph of G. So you select some of them out, into the to be the subgraph. So for example, 7a to graph H1 and H2 are subgraph of G, and 7b like B2, D3, and K3 are the subgraph of G. For example, B2. Which part is B2 is the subgraph of G? Is this one, right? Into here. You see that G has contained two self-loop. Two self-loop become the bouquet. Remember bouquet. Bouquet is like we have the self-loop, like B2, two self-loop here. If we have 4, like this petal flower, we have B4, like that, right? So this is B2. And we have D3. Dipole is this portion here, right? And K3, K3 is this portion here. So K3, D3, and B2 are the subgraph of G, depending on how you model those one. So in subgraph consideration, graph could be either labeled or unlabeled. If it is labeled, the identical labeling applies. However, if it's unlabeled, the subgraph must be part of the supergraph and has structurally preservation. That's why we mentioned about structurally preservation earlier.
Professor?
Yes.
We can say B2 as B4 because you in the previous lecture mentioned that the self loop is counted as 2. 1 plus 1, 2.
What do you mean? Sorry. Self loop is considered as
counted 2 times. 1 plus 1, 2. So in that case, it could be 4 because 2 self loops.
What do you mean? 2 self loop considered as 4? I'm not sure. If you have one self loop like this one, right? 4 degree for this node, right? And you see that in this one, we just only select this size, this portion here to be this subgraph.
Yeah, 2 self loops.
I can have this one. This one is also subgraph of G. D1. Because I only select this node and this one. So this is the subgraph of this one. I don't have to select all of them. Later on there will be some subcategory of the subgraph. That we will discuss that. So this one, if I say it is a subgraph of G, do you think?
Yes.
Yes, it could be this one, right? It could be this one, or it could be this one.
Yes.
Right? It could be anywhere.
Yes, Professor.
What about this one?
Yes.
Sir.
Yes. Okay. So this is the subgraph of G, right? Okay. What about this one?
Yes.
Yes. Okay. Because you see that we have this one, this one, this one, this one, this one, and this one. Okay. So this is subgraph of G. Okay. So this is concept of subgraph, but later on we will have something like proper subgraph and so on. Okay, so we consider what are those meaning. Okay, okay. Now we understand the concept of subgraph because many times we're gonna use subgraph concept to analyze the graph. Okay, and check various property of the graph. Okay, in later lecture. Okay, so subgraph check, isomorphic check, and automorphism check. Okay. So now we have something called spanning subgraph. Okay, we have the term spanning. Okay, spanning here, okay, have specific meaning. According to the subgraph definition, subgraph H, where we have the VH and EH here, is part of the graph G, where the big graph is VG and EG. You see that VH would be subset of VG and VEH would be the subset of EG. Okay, subset could be pure subset, okay, or equals to the to the superset. Okay, so VH may or may not contain the full member of VG. That is, VH would be the subset, or it could equals to VG. Okay, so that we use the subset and the equal signs at the bottom. Okay, subgraph H is said to span a graph G if VH is equals to VG. Okay, look at this definition. A subgraph H is said to span a graph G if VH is equals to VG. So in this one, we see that we require to have all nodes in G to appear in the subgraph H. Okay, for example, if we have the subgraph like 8A, 8A we have 8 nodes. Okay, 8 nodes here. We can build a tree among these 8 nodes, okay, as the bold line there. Okay, you see the bold line there are the subgraph of the original graph G. Let's say the graph G contains both bold lines and light lines, okay, but we select the bold lines to be our subgraph. And this subgraph cover every node in the original graph. Okay, so this we call spanning subgraph. If I have like this one, this is original graph fully connected, okay, K4. If I have this one, subgraph, let's say A. This is subgraph A is spanning subgraph of K4 because it covers 4 vertices of original graph. Okay, and somehow it might be connected, unconnected. Okay, so this one, we have the already a graph H2 span G, but H1 does not. Okay, I think we have to have H2 span G, but H1. Okay, in this one we have 1, 2, 3, 4, 5, 6, 7, 8. This is different. I didn't give you the complete picture. We have, hold on, H1, H2. This one should be 7A, sorry. Let's go back to here. Okay, let's correct this one, 7A. Okay, I'm sorry about this, a lot of misprint. I just rushed to produce this slide earlier. 7A. Okay, 7A, look back at this one. Okay, you see that graph H1 and H2. Okay, H1 and H2, here we have the H1 is a subset of G, and H2 is a subset of G as well. But you see that H2 have all the vertices in the G. We have 5 vertices, but the H1 has only 3 vertices. Okay, so H2 is considered to be spanning subgraph of G. Okay, but it might not contain every edge of G. You see the edge F disappear from H2. Okay, so this one, H2 is spans G, but H1 does not. So it can be seen from graph G that and H2 have the same set of vertices. Okay, that 5 vertices there. Once the graph is constructed, the spanning subgraph of original graph, the EH must present the subgraph may form a tree in this one. Okay, but it could not be a tree, but you can see the tree. Remember the tree. We're going to discuss tree next week. Okay, tree is a graph with no cycles. Okay, you see that it's 8 nodes here. Okay, have no cycle in the bold line. But if the light line included, okay, we're gonna have the loop. Okay, later on we're gonna consider the tree property. Okay, the tree property, there are very interesting property of tree that we're gonna discuss. Okay, spanning tree of a graph is a spanning subgraph that is a tree where a cyclic graph of multiple tree is called a forest. Okay, so we have this one. Okay, this 8 nodes here, 8 vertices, and we have all 8 nodes connected together into something called component. Okay, we're gonna see the term component later. Components are the set of graph that connected together, okay, with the link. Okay, but if you look on the right hand side, we have a forest. Okay, a forest comprised of multiple trees. You can see that the first component, the second component, the third component, and the fourth component. These 4 components cannot communicate or cannot move from one node to the other of different components because they don't have link join them. Okay, so this one, if you want to join them, okay, if you want to join them, you need to give like a link between those components, right? So this, we talk about components are the connected part of the graph. And in the first graph, you see that these things are one component because 8 nodes connected together. Okay, when it's connected together, they are considered as one component. Okay, okay, so this graph, okay, let's try this one. I'm not sure. Okay, we have, okay, this one, you see 4 different components. Okay, 1, 2, 3, and 4. What do we call this one? One node, single node. Do you remember we define a single node without edge? We call
null.
Trivial graph, right?
Null.
Okay, trivial graph is one node without an edge, right? Okay. Any question on the spanning subgraph?
Sir, can you go
Oh yes,
last
Professor, I have a
slide?
question.
Sorry, Asha.
Sir, can you go last slide? I have a question from
Last slide. This one?
Yes, sir. In H2, if we remove the edge B, then it is a spanning tree?
H1 or H2?
H2.
H2. In this one is not spanning tree. Spanning subgraph, but this not a tree. Why? There is a cycle here, right?
Okay, sir.
Okay, so it's spanning subgraph, but it's not spanning tree.
Okay, if we remove the D from U,
you can remove A, you can remove D, or you can remove C. Eventually, that would be spanning tree as well.
Okay.
Okay, so we can have something like this one, this one, this one, and this one. This would be spanning subgraph as well as spanning tree. Okay, because this is a tree.
Okay.
Sen, are you okay?
Professor, no, Professor, I have a question that in the next slide they are mentioned that.
Yeah. Okay.
Can you move to the next slide, please? You mentioned that graph H2 spans G, but H1 does not.
Oh, the right hand side is not span. The right hand side we call forest. Actually, it's if we have okay, let's try with this. This is edge A and edge B are two complete graph. Okay, two different graphs. Sorry, two different graphs, not two complete graphs. Two different graphs. Okay, the first one has 8 vertices. The right one has altogether 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 vertices. And you can see that 12 vertices might not need to be connected into one single component. But if I draw like this one, if I draw, okay, let's try the black pen. I have this one. This is spanning subgraph of original graph, right? Okay, because it's connected. Actually, this graph, if you have the original graph like this, I should say. Hold on, I'm sorry, I'll try to explain again. This is original graph. Let's say this is original graph. And I select this one. Like this. This is spanning subgraph original graph. Okay, spanning subgraph because it covers all the nodes of original graph, though it might not be one single component. So it's not 3, right? Because it's 4 components. It comprises of 4 components. And now we look at each component. In this one, we have 4 trees. Okay, so we call it forest. But if one of them is
two conditions to.
Sorry.
There are two conditions that it should be the subgraph of the spanning tree, and it should be a tree.
Okay, if you have a graph, okay, in order to be spanning subgraph, all the vertices must appear in this subgraph. Okay, though all the vertices might not be connected into a single one. If I have something like this is one component, right?
Yes, Professor.
Okay, but if I don't connect this one, don't connect this one, and don't connect this one, but we still have the link like that, but we didn't like this. This is 4 components. The first component, the second component, the third component, and the fourth component, right? Okay, but it's still spanning subgraph, right? Because it's covered, it appears to have all the vertices. And now we look at the definition of forest. You know, forest full of tree. So it means that forest must have several trees, okay, in the graph. Okay, so this one, it comprises of 4 trees. Okay, so 4 trees, and those is though it's not a single tree, we call forest. Okay.
So in the above example, in the back example, however, the H1 and H2 follows the graph G, but we still said that H2, the H2 does not.
You mean the previous page?
Yes.
Yeah. So what was your question?
That in the graph G, we have a component that was H1 that is fulfilling the graph G, and also H2. It is the same fulfilling the graph G, but we still rank it is not a spanning subgraph.
This H2 is spanning subgraph because it's all these nodes here appear in this node here. Okay.
Okay.
But it's not a tree because you see that this forms the cycle.
Yeah, there is a loop.
Yeah, so this is not a tree, but it's spanning subgraph. But if I draw like this one, This is spanning tree as well as spanning subgraph.
Understood, Professor.
Okay, so forest combines several trees or multiple trees. Okay. Okay, so this is spanning, and we have the term clique. Okay, actually clique, we're gonna talk about it again in coloring chapter. Okay, so clique, okay, is we have the vertices of a graph. Okay, is concept of clique. Okay, is opposite to the independent set of nodes. Okay, of this we have the term clique. Okay, let's look at the clique first, and then later on we're going to talk about the independent sets of nodes. Clique, a subset of S in VG is called clique. Every pair of vertices in S is joined by at least one edge, and no proper subset of S has this property. Basically, a clique in a graph is a complete subgraph of G. Okay, so think about clique. What could be clique from this 9A? Okay, what is complete graph? Complete graph, we can have order one is node itself. Complete graph of order two is two nodes joined with a link. Complete graph is of 3. Okay, complete graph of 3 is like that, right? Complete graph of 4 is this one, right? And so on. Okay, when we look at the subgraph of this original graph, what is the clique number of this graph? Look at this graph here. Okay, clique subset S of VG is called clique if every pair of vertices in S joined by at least one edge, and no proper superset of S has this property. Okay, so this one you look at, basically they say the clique is a graph of a graph is a complete subgraph of G. Okay, if I say 9A is a graph where there are three clique in this one. There are this one, the clique of order 3, right? This is one of them, and another one of them, and another one of them. Okay, what about UV? Is there a clique? Is this another clique or not?
Yes.
Why?
U and V are connected to each other.
Yeah, but remember we have that no proper superset of S has this property. So it means that if we can find bigger number of vertices that could form the clique, UV will not be the clique itself, because UV is a clique of order 2, right? 2 nodes, right? But we have U, V, and Y that contains U and V as well. So U, V, and Y is the clique size of 3. That's bigger than UV itself. UV is only 2, right? But Y and Z becomes the clique in itself because Y and Z, it doesn't belong or part of any superset that bigger. If I have this one, like let's say X, let's say A here. If I have this one, A, we're gonna have U, V, Y, one clique, right? And we have X, Y, X, U, X, Y, and we have Y, Z, A, right? This is 3 clique. What about if I have this one? How many clique do we found in this graph?
V, X, Y.
Okay, so we have 2, right? U,
Yes,
V, X, Y, and Y, Z, and A. Only 2 clique. Right? We're not going to list 3 nodes of the left-hand side clique because we have superset or the bigger set that would form bigger clique, right? UVXY would be size of 4, and we have full complete graph of UVXY. So UVY or UXY gonna be part of the UVXY, right? Or you can have, in this case, you can have UXV is part of UVXY as well. Okay, so we just take the bigger one. Agree? Clear? This one. Any question?
Mean we have to find a complete graph. Either it is a for 2
That's
nodes,
right.
3
You
nodes,
have
or
to
4
look.
nodes.
Yeah, you have to look at complete graph in the graph, in the big graph. Okay. So, but sometimes you see that we have the clique of 2, the clique of 3, the clique of 4, and so on. But the biggest one, okay, we say that the clique number of graph G is the number of omega G of vertices in the largest clique of G. So in this graph, okay, in this graph 9a, the clique number is 3, right? The order of largest clique. But if I have this one, like now, right now, just now, what is the clique number of this graph?
4.
4, right? So 4. So this one clique number is 4. So we take this one as the clique number of this graph. Okay, but if I ask you how many clique in this graph, you just take different complete subgraph out. Okay, so we have 1 4 clique, okay, and 1 3 clique. Okay. Any question?
Okay, sir.
Okay, good. Okay. Okay, let's move on to this one where I have the induced subgraph. Induced subgraph. What is induced subgraph? Remember, we have subgraph is the when a subgraph is generated, if H is the subset of the G, okay, and either VH is a proper subset of VG or EH is a proper subset of EH, then H is a proper subgraph of G. Okay, so in this one, what is the definition of induced subgraph? Can you think of? For a given graph G here, you can notice from 10A to 10B. Okay, so in this one, you see that we have the subset of subgraph of 10A to be 10B. Okay, surely the bold line in 10B is a subgraph of 10A, right? But in this one, we call it the induced subgraph. What's the induced subgraph in your opinion? For a given graph G, the subgraph induced on vertex subset U of VG, denote GU, is a subgraph of G whose vertex set is U and whose edge set consists of all edge in G that have at both endpoints in U. Okay, all edges in G must appear in the subgraph as well. Okay, so this one you can see if you have original graph is the U, V, and W as 3 nodes, and we have link A, B, C, D, E, A, B, C, D, H, F, G. This is the all edges. But if your subgraph includes V and U, all the links or all the edges that have U and V as endpoints must be included in the subgraph. So we call this the induced subgraph. Okay, if I have the V and W in subgraph, what is the VW would look like? We have VW, right? So your induced subgraph should be like this.
In V and W. Yes.
G, right? This is going to be induced subgraph. So V and W will be the endpoints in the subgraph. So all the edges that appear having V and W, okay, in the original graph, all those edges must be part of the subgraph that you induced. What about if we have U, V, and W? What's induced subgraph? It will be like original graph, right? It will be the same graph, right? Because you have to include everything in your subgraph. Okay, so this special, sorry, Imran, you said, okay?
As you said that UVW is the same graph, but
yeah.
U will include C.
Yeah, because if you have U, V, and W in the subgraph, in order to be induced subgraph, you have to include all the edges, because now this is the spanning, right? It spans to all vertices in the original graph. So induced subgraph must include all edges in G, okay, that have both endpoints in U, right? Okay, so now we're going to have all the edges that appear in original graph in the induced subgraph here, because we have all the members of vertices in the original graph UVW. Okay, so this is induced subgraph. Okay, what about this local subgraph? Okay, check this one. Okay, we have local subgraph is subgraph concept that considers relationship with surrounded vertices. Set of vertices that are adjacent to the considered vertices are listed here. Okay, so local subgraph we represent by L. Okay, local subgraph, we have to specify what are the vertex that you are considering to be local to that vertex. For example, LU, what is local to U? And LV, what is local to vertex V? Okay, so local means we have to look at who are the neighbors of that particular node or adjacent to that particular node. Okay, look at the original graph is G. When you have LU, you look at U. U is here, right? So let's look at the original graph. U is here. So neighbor of U are this one, and this one. Okay, and find the induced subgraph of these three green nodes. We've got LU, the second graph. Okay, look at LV. LV, we have LV here. We have V here. What is the neighbor or the adjacent to V? Adjacent to V is this one, this one, this one, and this one. Right? So according to these four green nodes, what are the subset induced from this one? You see that the node itself is not included in the subgraph, only the neighbors or neighborhood of this one. So we have U, okay, included, and three nodes here. So the graph that appears, okay, to among these four nodes would be this one. And this one is like standalone. Okay, what about outer set, Imran? Yes.
We can simply say that we will only include the nearest neighbors.
Not the nearest, all the neighbors. Yeah, all the neighbors. Yeah, all the adjacent nodes.
All the neighbors that are directly connected to the node.
Yeah, that is have the edge connected to that node. Okay, for example, if I have the set here, what is the L set? I have to consider what is the member of that is sorry, neighbor of that is this one, and this one, and this one, right? This is the neighbor of that, and the induced subgraph of these neighbors are this one, this one, this one, and this one, right? Okay, this is L set. Okay, whereas that is on the right. Okay, so this is local subgraph. Okay, induce on the neighbors of V. Induce means all the edges appear in original graph and endpoints are these nodes, okay, must be included in the subgraph. Okay. 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 Okay, now components. Okay, we have talked about components. Okay, we can go quickly on this one. Some vertices or edges of graph G that is earlier connected as one connected graph, okay, have been removed and cause G to be broken down into small parts. We call these small parts a component. Okay, component of a graph is maximal connected subgraph of G. Alternatively, a connected subgraph is of H is component of G if H is not a proper subgraph of any connected subgraph of G. Okay, so this one we will talk about the components. I think you can grab the idea of components very quickly. Okay, that all the nodes or vertices in that component must be connected together over the link. Okay, and if you cannot communicate or find the transversal from one node to the other, we say that those two nodes are on different components. Okay, so the component of vertex V, okay, denoted CV, is the subgraph induced by the subset of all vertices reachable from V. Okay, reachable from V. So this one we're going to induce the subgraph together with subset of all vertices reachable from V. So if V is here, the reachable from V is this one and this one, right? Okay, it means that we are connected with that node. Okay, so vertex V that is reachable from V from U if there is a walk from U to V. Okay, if you have U here, you can see U and V has no walk towards each other because they are on different components. Okay, one could appreciate the fact that by now the vertices within the same component are reachable from one another, given that we have undirected edge, right? Okay, but if we assign the edge to the arc, okay, we surely see some cases that we might not be able to reach another node if you don't have the arrow sign linking towards that node. But in case of undirected, okay, we should have walk, okay, from one node to the other node if they are connected in one component. Okay, if you are on different components, you will not be reachable to one another. Okay. Okay, so let's look on this one. Some graph operation that we talk about here. We talk about the deleting vertex or deleting edge or multiple vertices or edges. Okay, when deleting the vertex, all the edges connected to it must be deleted as well. Okay, so vertex deletion subgraph, okay, is a subgraph induced by the vertex set VG. Okay, V subscript G, sorry, V subscript G minus node V or vertex V. So for example, in this one, we have U, V, and W. If you remove or delete W, okay, we're gonna have the subgraph induced from that deletion. So I mean all the link connected to W will disappear as well, and the remaining still there. Okay, remaining still included in the induced subgraph. Okay, but if it's edge deletion subgraph, you can see less severe of the effect, okay, from that deletion. Okay, now we can talk about the network vulnerability that we'll discuss shortly in the next slides.
Professor?
Yes, Sen.
I think so. There is a mistake in the definition.
Yeah, sorry, which one?
You mentioned that the vertex set VG minus V.
Yeah.
However, it would be W.
It should be,
because
because in this example, this example delete W, but I think definition is deletion of V, but it's not applied directly to this example. Okay, if I have deletion of V, okay, by definition I use just V and E to represent the vertex.
V as a vertex. Okay. V as a vertex.
Sorry about this. Okay, just it could cause confusion. What about this one? If I have deletion of V, what would be the graph? It would be
the edge would
U,
be towards W.
W, right? And we should have D left, and we should have B and A, right? Okay, all the link connected to V nodes will disappear, right? C, H, F, and G will disappear. Okay, so this is the induced subgraph when you delete the vertex B or delete vertex U. What about delete vertex U?
Then it will go to V to W only.
Okay, so it would be something like this left, right?
Yes.
Okay, good. Okay, what about edge deletion subgraph? You just delete the edge. Very basically, you, for example, you delete E. Okay, delete this one, delete F. The example, delete F, right? So F disappear. So you have this one. Okay, E represents H and small v represents vertex or any vertex. Okay, so we have the concept of network vulnerability. Okay, so this one, when you look at the graph, we have the vertex cut and cut vertex, and edge cut and cut edge. So these are four things that you have to identify from this graph. Vertex cut. Okay, we should have a graph G is a vertex set U such that the removal of U from original graph will cause more components than G or disconnect. Okay, you see that in this original graph, everything connect together into one component. But once you remove a set of nodes, okay, more than one node, okay, we're gonna have the disconnection. Okay, but we have special case that we call cut vertex. Cut vertex is only one node removal, one vertex removal will cause the disconnection. Okay, it means the vertex cut that we are talking about in the previous case consists of one single vertex. Which one are the cut vertex in this graph? Removal of
node,
one node, right? So
last node.
What's node that would be removed?
That it is black node after Z node.
The white node actually cut vertex, right? The black
because
nodes
if we cut the Y, then it is two components.
Yeah, of course. Yeah, so W, X, Y, and Z are the cut vertex. Okay, and for example, if you remove U and V, that's vertex cut, right? If you remove U and V here, U and V in itself is not cut vertex, but it's vertex cut if you remove U and V together. Okay, U and V would be the vertex cut. Because if you remove this one, you're going to eliminate all the edges connected to it. Okay.
Professor?
Yes.
Yes. So we can say in this scenario that the vertex cut is in the single graph, and the cut vertex connects two graphs.
Vertex cut could be multiple vertex. That removal could cause disconnection, whereas the cut vertex is the single node removal and cause the disconnection. You see that if we use in English word, okay, it is noun, right? And this is adjective, right? Okay, so cut means we have, we have multiple vertex and single vertex, or edge cut is like we have a set of edge that could cause the cut, whereas cut edge is like a single edge that caused the cut. Agree? Okay, what are the cut edge in this graph? UW is the cut edge. UW, this one is the edge, right? This one is a cut edge.
Yes, sir.
Sure. Because you can see that if you remove this one, we can still go that with this link, right? So it's not cut edge. But UW and VW is the edge cut. So a set of edge whose removal would cause disconnection. If you cut these two edges, like this one and this one, this would be edge cut. Okay, UW and VW is the edge cut. What about cut edge? Do you find cut edge here?
WX.
How many cut edge do we have in this one? Let's try to give the label to all of them. How many cut edge do you find? Mia, are you there? You're so quiet. ณภัทรด้วยครับ อยู่ไหม
Yes, I'm here.
Mia, do you how many cut edge do you find in this graph?
I think 3.
3. Which one? Tell me.
W to X.
W to X, right?
And Y to Z.
Okay, good.
And F to Z.
Okay, see Z and F, right?
Yes.
So 3. Okay, good. ณภัทร โอเคไหมครับ how many cut vertex ครับ ณภัทร อยู่ไหม
อยู่ครับ
ครับ ณภัทร how many cut vertex do we have in this graph? Cut vertex.
W
W X, right? X is also cut
Yes.
vertex. Y
and Z.
and Z. Okay, Z. Okay. So in this one we have 4 cut vertex. Okay. If I ask you let's try if I have X D and Y E, are these the cut edge or not? Sorry, the edge cut or not?
Not
Yes.
because we have a DE.
Yeah, because if you cut this one and you cut this one, you're still okay with this, right? So it's not disconnect. But if you have XD, so this is not the edge cut. What about the XG and XE?
Then it will be.
That will be
Yeah, then
edge
it will be
cut,
edge
right?
cut.
Okay, this is edge cut. What about DE?
No.
No, it's still
No,
okay
we
because if you
still
cut this
have-
edge, it can go this one or can go this one, right? Okay, so this we can consider the graph and talking about the subgraph if some of the edge or some of the node has been removed. So when you design network in communication data centers or something like that, we may have to look at this issue of the importance of various location or the link that vulnerable to attack. Okay, so in this one, in order to eliminate the later on, if I want to talk about application of this network vulnerability, how many links you have to add to eliminate the cut vertex? The minimum number of links that you add to eliminate the cut vertex.
I think if we connect V to E and E to F.
V to E.
Yes. V to E and E
Yep.
to F.
Yeah. Is that can anyone find lower than this? Okay, so this one you can see if we add 2 edges, we could have no vertex, no cut vertex, right? Okay, so 2 edges must be added at least to have no cut vertex on reduced vulnerability of your design. Okay, because we have alternative ways of delivering or communicate with other nodes. Okay, without a single point of attack. Okay, we may say single point of failure. Okay, a single point of failure causes disconnection. Okay, that could happen. Okay, so this is the minimum, but you can add more. Okay, like you can add more like this to add more more alternatives or the survivability of the network. Okay, but if you want the minimum requirement to have no cut vertex, okay, maybe you can have, what about this one? Do we still have the, like this too? Do we still have cut vertex?
Yes.
If you remove.
Yes, sir.
Yeah. Which one is the cut vertex?
Sir, F2Z.
Yeah, if you remove that, okay, F will be disconnected, right? Okay, so that would become the only cut vertex of this graph. So not just the amount of link being added is where too, okay, would be important as well, okay, in your design, okay, in your consideration. So graph theory would help you realizing how you draw, how you design the location of link, okay, who to be connected, okay, and how that would be after you run the operation. Okay, so reconstruction is like the another issue that we're talking about, okay, is reconstructing the graph, okay, based on various, okay, deletion of the graph. Okay, for example, if we have a graph G, okay, reconstruction problem could be easy to solve if graph has been deleted. Okay, so this one, if you remove a certain node out of this graph, okay, what would be the remaining graph? Okay, the outcome of the after this deletion of this. Okay, are you okay with this one? Okay, just vertex deletion subgraph list. If you remove a certain node, okay. Okay, so this is like you remove remove U, remove V, remove W to remove X and remove Y. Okay.
Yes, it's the simple one as we discussed earlier.
Yeah. Okay, this is simple. Just like the problem of the reconstruction. Okay, that is just what we mentioned a little bit on this one. Okay, and test for non-isomorphism. Another thing is if we have mentioned about the apart from what we have discussed so far, okay, you can see that we have mentioned most problem of graph theory concerned with identifying whether a several graphs are isomorphic or not. Okay, in order to state their isomorphism, we test on the number of vertex, the number of edges, and the degree, okay, adjacency and non-adjacency. Okay, if you have two or more graphs to be alternatively analyzed for its non-variant non-isomorphism, we have all known that the number of vertices and edges and degree sequence are the same for any two isomorphism graph. Okay, look at this particular case here. This example, sorry, a graph invariant, okay, or digraph invariant, okay, that is preserved by isomorphism as well. Okay, so check out this one. Do we have the graph that would maintain the degree sequence like 16A graph G and H? Same number of nodes, number of degree sequence. Are they the same degree sequence? Degree sequence, normally you can write like increasing order or decreasing order. In this one example on the bottom left is the increasing order, right? 1, 1, 1, 2, 2, 3. Or you can write 3, 2, 2, 1, 1, 1. Okay, it's up to you. Okay, but in this both graph we have 1, 1, 1, 2, 2, 3, right? But these two graphs G and H are non-isomorphic. Okay, can you spot that they are not, obviously they are not isomorphic, right? What about degree sequence? Are they the same? These two graphs G and H share the same degree sequence, right? Okay, but because this is simple graph, very few number of nodes, you can see that Obviously, it is not the same graph. You can see if you map the nodes, okay, here, the distance between two nodes must be the same when you map them. Okay, so theorem said that when you mapping G to H to be a graph isomorphism, let V be the vertex in G, then the multiset of degree of neighbors of V equals to multiset of degree of neighbor of FV. Okay, so now we talk about the, if we have, this is another consideration further from what we have discussed earlier, that when you have the neighbors, for example, V here and W here is the point of 3 degree, right? The neighbors of V has 1 degree, 1 degree, and 2 degree. Okay, but the neighbors of 3 degree here, we have 2 degree, 1 degree, and 2 degree, which is different. Okay, so this is the point of graph invariant. Okay, graph invariance mean in this theorem they say multiset of degrees of neighbors of V equals to multiset of degrees of the neighbor of FV. Okay, so you see that V and W seems to be mapped, must be mapped the same, right? Because this is the only one node that have 3 degree. So if we want to have the bijection of this node, V and W must be mapped to each other because it's the only 3 degree nodes. Okay, but neighbor of V and neighbor of W didn't provide the invariant property. Okay, because neighbor of V has 1, 1, and 2 degree, and neighbor of W has 2, 1, 2 degree. Okay, you okay with this? Okay, apart from the degree of neighbors, okay, we can talk about the distance invariance as well. Okay, I think we run out of time somehow. I don't want to stay longer than 4 o'clock. Okay, so I think we have only few pages left, about 8 pages. So I don't think we're gonna go through, okay, all of them. I'll leave it for now, and then we'll continue this set of notes, okay, next week before we move on to tree topology, okay, tree network on the lecture 3. I will upload 3 into the My Course View, and you can download that before next class. Okay, so are there any questions from the lecture so far? Okay, you can read this slide before we become next week, so we can go a little bit quicker, or you have any question in advance, we can discuss that. Yep. Okay, so I'll call it a day today. We have almost 4 now. Okay, I'll upload this video into the into MS Teams. You can review later when you need it to. Okay, I'll see you next week on Wednesday afternoon. Okay, take good care of yourself. Okay, and
Okay, Professor.
Thank you.
Thank you, sir.
okay,
Have a great day.
thank you.